Often, scientific discoveries arrive as small, subtle things, a slight dip in a star's brightness, a ghostly signature tucked away in a light spectrum, or a faint whisper of gas drifting across a sensor. But every so often, the universe delivers a signal so profound that it freezes the scientific community in its tracks. It is a signal that forces us to face a staggering possibility. We might no longer be searching for life, but looking right at it. Located just 40 light-years away, orbiting a cold, ancient red dwarf star barely bigger than Jupiter, sits a planet that has ignited one of the fiercest scientific debates of our era. This is TRAPPIST-1e. It is a rocky world situated perfectly within its star's habitable zone. Recently, the James Webb Space Telescope, JWST, probed its atmosphere with a level of precision never before achieved. The resulting layers of spectral data suggest something extraordinary, something we hardly dared to dream. For the first time, we may be staring at a world possessing all the essential ingredients for life. It is a place where oceans might persist, where chemistry could thrive, and where the night sky is illuminated by a star looming 4 times larger than our sun appears to us. Tonight, we explore why TRAPPIST-1e has captivated every astronomer on Earth, how the James Webb Telescope pushed its limits to read its sky, and what this evidence truly tells us about life beyond our solar system. The cosmic jackpot. When astronomers first trained their optics on the faint red ember known as TRAPPIST-1, expectations were low. It is an M8 class red dwarf, a dim bulb radiating only 1/1800th the brightness of our sun, cold, old, and seemingly unremarkable. Yet, hidden beneath that stillness was a cosmic jackpot unlike any other. Astronomers began detecting tiny, rhythmic dips in the star's light. These were signals of planets crossing the star's face. They soon realized they hadn't found just one candidate for habitability, but an entire family. They had discovered 7 Earth-sized, rocky worlds, all orbiting closer to their star than Mercury does to the Sun. They are locked in such a tight gravitational embrace that one face of each planet is forever fixed toward the star. Initially, experts wrote the system off as hostile. Red dwarfs are infamous for violent magnetic storms, extreme flares, and chaotic radiation capable of shredding an atmosphere before life can even start. But TRAPPIST-1e refused to be dismissed. Its orbit lands at dead center in the habitable zone, receiving roughly 66% of the light Earth gets, just enough to sustain liquid water, provided it can hold onto a stable atmosphere. That single condition became the driving force behind one of the most ambitious observation campaigns in the history of exoplanet science. TRAPPIST-1e isn't just another rock. It is the most promising Earth-like analog we have ever found. The JWST investigation. When NASA opened up early observation time for the James Webb Space Telescope, the DREAMS collaboration, a team with guaranteed access, made an immediate, bold choice. They pointed the most powerful telescope in history directly at TRAPPIST-1e. Their objective was simple but audacious: find out if this distant, small world actually has an atmosphere. To achieve this, they utilized transmission spectroscopy. This delicate technique measures how a planet's atmosphere filters and absorbs tiny slices of starlight as it passes in front of its host star. For most exoplanets, this is nearly impossible. However, TRAPPIST-1 provided a unique advantage. Because the star is so small and dim, the planet blocks a surprisingly large percentage of light, creating a much stronger signal than we would see around a sun-like star. Webb's NIRIS instrument captured the wavelengths absorbed during 4 separate transits. The initial data immediately ruled out several scenarios. The planet does not possess a puffy, primordial hydrogen-helium atmosphere. The red dwarf's radiation would have stripped that away eons ago. It also lacks a thick, Venus-like carbon dioxide blanket or a thin, dying atmosphere like Mars. With those ruled out, a compelling possibility remains. TRAPPIST-1e might possess an Earth-like atmosphere, dominated by nitrogen and supported by greenhouse gases like methane, carbon dioxide, or water vapor. If such an atmosphere exists at around 1 bar of pressure, it could circulate heat to the planet's dark side, allowing a global ocean to survive beneath skies divided forever between eternal day and endless night. This was the moment scientists cautiously began to whisper that this world might be more than habitable. It might be alive. The challenge of eternal twilight. However, an atmosphere doesn't guarantee a living world. Being so close to its star, TRAPPIST-1e is almost certainly tidally locked, with one hemisphere scorching in perpetual daylight and the other frozen in darkness. The urgent question was whether the planet could distribute heat well enough to prevent climate collapse. Webb's data offered clues, but no guarantees. If the atmosphere is too heavy in methane, the greenhouse effect could invert, cooling the surface and trapping liquid water only on the day side. Rather than a global ocean, TRAPPIST-1e might host a hemisphere-locked sea, a warm pool where prebiotic chemistry cooks beneath a red-orange sky. Simulations suggest another option. Life might flourish along the terminator, the thin ring of perpetual twilight that separates day from night. This narrow strip offers a stable climate known as terminator habitability. Others propose an even more exotic scenario, an icy, volcanic world with a subsurface ocean, much like Enceladus or Europa. Here, hydrothermal vents could serve as nurseries for life, shielded by kilometers of ice. Regardless of the specific environment, the implication is profound. TRAPPIST-1e may not be a clone of Earth. It might be stranger, more alien, yet fully capable of hosting life. The red dwarf paradox, the most dangerous and essential factor in TRAPPIST-1e's story, is the star itself. TRAPPIST-1 is a volatile red dwarf. Its flares dwarf anything our sun produces. The Carrington event, the strongest geomagnetic storm in Earth's history, would be a routine occurrence here, happening on average every 2 days. Such storms launch torrents of radiation that can strip atmospheres molecule by molecule, turning potential Edens into barren rocks. Paradoxically, this violence might be required for life. UV radiation is critical for forming the building blocks of RNA. Furthermore, TRAPPIST-1 is much calmer now than in its youth. There is a window for life to emerge, provided the planet has protection. A molten iron core could generate a magnetic field to deflect the stellar wind, assisted by tidal forces that knead the planet's interior, injecting heat similar to how Jupiter's gravity keeps its moon Io volcanically active. The engine beneath the crust, even if the surface is frozen, TRAPPIST-1e may hide a secret advantage: tidal heating. Due to its tight, potentially eccentric orbit, the planet is constantly squeezed and stretched by the gravitational pull of its 6 siblings. This flexing generates internal heat, estimated at 18 cents/text, W/m, which is 24 times the tidal heat Earth receives. This isn't just a geological footnote. This internal engine could keep subsurface water liquid, drive chemical reactions, and fuel volcanism that replenishes atmospheric gases like nitrogen and carbon dioxide. Tidal heating could be the planet's heartbeat, keeping it alive even if the starlight fails. The waiting game. We are currently in a scientific cliffhanger. James Webb's early spectral readings show neither a thick carbon dioxide signature nor a hydrogen envelope. Instead, they reveal a faint, ambiguous spectral silence. This is actually promising. A dense, nitrogen-rich atmosphere like Earth's would leave exactly this kind of subtle fingerprint. Scientists have scheduled 15 more transits. They are pushing the noise floor down, looking for consistent signatures of methane, carbon dioxide, or water vapor. If they find them, it confirms a secondary atmosphere. If they find spectral patterns matching Earth's, TRAPPIST-1e becomes the primary candidate for life in the universe. Conclusion: TRAPPIST-1e is one of the most extraordinary worlds we have ever found, not because it guarantees life, but because it refuses to answer no. It is a world of extremes, half-scorched, half-frozen, orbiting a star so old its lifespan makes the current age of the universe look like a blink. TRAPPIST-1e might be a silent graveyard, stripped bare by its star's violent youth. Or it could be a thriving haven, protected by a magnetic field, warmed by tidal heat, and evolving beneath a twilight sky. For the first time, we aren't looking at theoretical models. We are staring at a real, rocky world 40 light-years away. The answer is coming, slowly and inevitably. Maybe it will disappoint us. Or maybe, just maybe, it will be the place where we point and say, there. Life exists there. If you want to be here when the answer drops, make sure you are subscribed. We are closer than ever to answering humanity's oldest question. In the vast, silent expanse of the cosmos, the most earth-shattering revelations often arrive not with a bang, but with a whisper. A microscopic dip in a star's brightness that lasts for mere hours. A ghostly chemical signature buried deep within a spectrum of light. A faint trace of gas drifting across the detectors of a telescope millions of miles away. These discoveries feel small at first glance, mere data points in an endless sea of noise. But every so often, the universe presents us with a signal so profound, so jarring, that it freezes the scientific community in place. It is a signal that forces us to confront a possibility that has haunted humanity since we first looked up, that we may no longer be searching for the footprints of life, but staring directly at the creature itself. Located just 40 light-years from Earth, a stone's throw in galactic terms, orbiting a cold, ancient red dwarf star barely larger than Jupiter, lies a planet that has become the absolute center of one of the fiercest scientific debates of our time. This is TRAPPIST 1e. It is a rocky world, sitting perfectly within the Goldilocks habitable zone of its star. It is a planet whose atmosphere has now been probed by the James Webb Space Telescope with a level of precision that was previously the stuff of science fiction. And the results, layer upon layer of complex spectral data, suggest something extraordinary. They suggest something we have feared to dream about too loudly, lest we wake up. For the first time in history, we may be staring at a planet possessing all the key ingredients for life. We are looking at a world where oceans could be churning, where complex chemistry could be flourishing, and where the night sky glows beneath a star that looms 4 times larger than our sun appears from Earth. It is a world with a chance, however small, however staggering, of being alive. Tonight, we are going to dive deep into why TRAPPIST 1e has captured the imagination of every astronomer on Earth, how the James Webb Telescope pushed itself to the absolute breaking point to read its sky, and what this evidence truly means for our place in the universe. The cosmic jackpot. When scientists first trained their optics on the faint red ember known as TRAPPIST 1, nobody expected to find history. It is an M8 class red dwarf, a star so dim and small that it radiates just 1/1800th the brightness of our sun. It is cold, it is ancient, and by all stellar standards, it seemed entirely unremarkable. But hidden beneath that stillness lay a cosmic jackpot unlike anything discovered in the history of astronomy. One by one, astronomers began to detect tiny, rhythmic dips in the star's light, silhouettes passing in front of the flame. Soon, they realized they weren't looking at a single habitable candidate, or even a random pairing. They had found an entire family, 7 Earth-sized, rocky worlds, all orbiting closer to their star than Mercury orbits ours. This system is so compact that if you stood on the surface of one planet, you would see its neighbors hanging in the sky, large and detailed, like moons. Each of these worlds is locked in a gravitational embrace so tight that the same face of each planet is forever fixed toward the star, a phenomenon known as tidal locking. At first, many experts dismissed the system as hostile, a dead end. Red dwarfs are notorious for their temper. They are prone to extreme flares, violent magnetic storms, and chaotic radiation that can rip delicate atmospheres apart before life ever has a chance to spark. But TRAPPIST 1e refused to be ruled out. Its orbit places it in the exact geometric center of the star's habitable zone. It receives about 66% of the light Earth receives, a crucial amount that is close enough to sustain liquid water, if, and only if, the planet manages to hold on to a stable atmosphere. That singular if became the driving force behind one of the most ambitious observation campaigns in the history of exoplanet science. Because TRAPPIST 1e is not just another rock floating in the dark. It is the single most promising Earth-like world ever found around another star. The James Webb investigation. When NASA finally granted early observation time for the James Webb Space Telescope, JWST, one of the teams with guaranteed access, the DREAMS collaboration, made an immediate, decisive choice. They aimed the world's most powerful, gold-plated eye directly at TRAPPIST-1e. Their goal was both simple and audacious: to determine whether this small, distant world had any atmosphere at all, or if it was just a naked rock exposed to the vacuum. To achieve this, they utilized a technique called transmission spectroscopy. It is a method so delicate that it relies on measuring how a planet's thin layer of atmosphere filters and absorbs tiny slices of starlight as the planet passes in front of its sun. For most exoplanets, this task is nearly impossible due to the blinding glare of the host star. But the TRAPPIST-1 system offered a strange, strategic advantage. Because the star is so small and so dim, any planet passing in front of it blocks an unusually large percentage of its light, producing a signal much stronger than we would ever see around a sun-like star. Webb's NIRISS instrument recorded the wavelengths absorbed during 4 separate transits of TRAPPIST-1e. The initial findings were a process of elimination, ruling out the extremes immediately. The planet does not have a puffy, primordial hydrogen-helium atmosphere. The radiation from the red dwarf would have blown such a light envelope away eons ago. It does not have a Venus-like carbon dioxide blanket, crushing the surface under immense heat and pressure. Nor does it seem to have a thin, dying wisp of an atmosphere like Mars. With these scenarios eliminated, what remained was the possibility that TRAPPIST-1e possesses something far more compelling: a secondary atmosphere. This would be an Earth-like shield, potentially dominated by heavy molecules like nitrogen, with greenhouse contributors like water vapor, methane, or carbon dioxide in smaller, life-supporting quantities. If such an atmosphere exists at roughly 1 bar of pressure, similar to Earth's, it would be fully capable of circulating heat. It could transport warmth from the scorching day side to the frozen dark side, allowing a global ocean to exist beneath skies permanently split between eternal day and endless night. This was the first moment scientists began to whisper quietly, cautiously, that this world might be more than just habitable. It might be breathing. The challenge of the eternal day. However, we must be careful. An atmosphere alone doesn't guarantee a living world. Because TRAPPIST-1e is so close to its star, it is almost certainly tidally locked. This means one hemisphere faces perpetual, scorching daylight, while the other exists in a frozen, everlasting darkness. The question scientists raced to answer was whether this world could distribute heat effectively enough to avoid catastrophic extremes. Webb's data offered clues, but not certainty. If the planet's atmosphere is dominated too heavily by methane, the greenhouse effect could invert itself, cooling the surface and restricting liquid water to the daylit side only. Instead of a global ocean, TRAPPIST-1e might host a large iris of water, a hemisphere-bound sea facing the star, the kind of environment where prebiotic chemistry could flourish in warm pools beneath a red-orange sky. Simulations have shown another fascinating possibility. Life could thrive along the terminator. This is the thin ring of everlasting twilight separating day from night, a narrow but stable climate strip known as terminator habitability. In this zone, the sun never rises and never sets. It simply hangs on the horizon, bathing the landscape in perpetual dusk. Others have suggested an even more exotic scenario. TRAPPIST-1e could be an icy, volcanic world with a subsurface ocean, similar to Jupiter's moon Europa or Saturn's Enceladus. In such a world, hydrothermal vents could act as cradles for emerging organisms, shielded by kilometers of ice, just as some scientists believe happened on early Earth. No matter which environment is correct, the implications are profound. TRAPPIST-1e may not be a simple Earth clone. It may be something stranger, more alien, more varied, yet still absolutely capable of sustaining life. The red dwarf paradox. Of all the factors shaping TRAPPIST-1e's chance at life, none is more dangerous or more essential than the star it orbits. TRAPPIST-1 is a volatile red dwarf, and its history is violent. The strongest geomagnetic storm in Earth's recorded history, the Carrington event of 1859, fried telegraph wires and set the sky ablaze. On TRAPPIST-1, a storm of that magnitude is estimated to happen every 2 days on average. Such storms unleash torrents of X-ray and UV radiation capable of stripping atmospheres away molecule by molecule, potentially turning promising worlds into barren, irradiated rocks even after oceans form and life begins. This is the great filter of the red dwarf. But paradoxically, those same flares may be necessary for life's origin. Ultraviolet radiation plays a critical role in the synthesis of RNA building blocks, the fundamental molecules behind every organism we know. Furthermore, TRAPPIST-1 is far calmer today than in its violent youth. It has entered a long period of stability, offering a potential window where life could emerge and be maintained, provided the planet has some form of protection. And TRAPPIST-1e might indeed possess that protection. A molten iron core could generate a magnetic field strong enough to deflect the stellar wind, shielding the atmosphere. This magnetic field could be powered by tidal forces constantly kneading the planet's interior, injecting heat and keeping the core molten, much like Jupiter's moon Io, which is sculpted into perpetual volcanic activity by gravitational stretching. Combine a magnetic field, a resilient atmosphere, a heat distribution system, and potential water, and suddenly the odds tilt toward a world that is not only habitable, but shockingly resilient. The engine beneath the crust. Even if the surface of TRAPPIST-1e is cold or partially frozen, the planet may hold a secret weapon deep beneath its crust, tidal heating. Because of its close and potentially eccentric orbit, TRAPPIST-1e is stretched and squeezed by the gravitational pull of its neighbors in the seven-planet system. This constant flexing creates friction deep inside the rock, injecting internal heat into the planet. Scientists estimate this mechanism could generate 0.18 watts per square meter of internal heating. That is 24 times more internal heat than Earth receives from tidal forces. This is not merely a geological curiosity. Internal heat can keep water liquid beneath an icy shell, drive chemical reactions, and support entire ecosystems without a single ray of sunlight, just as hydrothermal vents sustain life in Earth's deepest trenches. If TRAPPIST-1e has volcanic activity, it could continuously replenish atmospheric gases like carbon dioxide, methane, or nitrogen, gases that James Webb is precisely looking for. Tidal heating could therefore be the planet's heartbeat, a hidden engine that keeps it alive even when starlight fails. The razor's edge of discovery. James Webb has delivered the first hints of TRAPPIST-1e's atmospheric composition, but the document makes it clear the real breakthrough hasn't happened yet. Scientists have already scheduled 15 additional transits. Each one allows Webb to collect more precise spectral data, stacking the observations on top of one another to push the noise floor lower and lower until doubt collapses into certainty. These transits are not routine observations. They are the most ambitious campaign ever undertaken to characterize the atmosphere of a rocky exoplanet. The data is currently balanced on a razor's edge. If Webb detects carbon dioxide, methane, or nitrogen with consistent signatures, it will confirm the presence of a secondary atmosphere, a monumental step in assessing habitability. If water vapor is detected, even in small quantities, the implications would be historic. And if the spectral patterns match those of a stable, Earth-like atmosphere, then TRAPPIST-1e will become the most compelling life candidate humanity has ever found. But the suspense is not only scientific, it is existential. Each transit deepens the tension. Will this planet be revealed as a cold, dead sphere, stripped bare by its star? Or will it reveal itself as a living world with climates, oceans, chemistry, and perhaps biology evolving beneath a dark red sky? The final question. In the end, TRAPPIST-1e stands as one of the most extraordinary worlds humanity has ever discovered. Not because it guarantees life, but because it refuses to let the question die. It is a world that exists in perpetual extremes, one half scorched by endless daylight, the other locked in eternal night, yet still finds ways, through atmosphere or ocean or tidal heat, to remain possible. It is a world orbiting a star so ancient that it will continue to burn for 10 trillion years, far longer than the current age of the universe. This means that if life has taken hold there, it has had eons to evolve, and will have eons more to continue. TRAPPIST-1e could be a thriving haven or a silent graveyard. But this uncertainty is precisely what makes it breathtaking. For the first time in history, we are not staring at vague hints or theoretical models. We are staring at a real world. A rocky, Earth-sized planet 40 light-years away whose atmosphere is within our reach to confirm. A planet where chemistry could be stirring right now. A planet that may be writing its own version of life at this very moment. And with 15 more James Webb transits on the way, the answer is coming. Slowly, quietly, inevitably. Maybe TRAPPIST, 1E will disappoint us. Maybe its surface is barren, cold, and airless. Or maybe, just maybe, it will become the first world in human history where we can point to a speck of light in the sky and say, there. Life exists there. And when that moment comes, everything changes. Our science, our future, our understanding of the universe and of ourselves. If you want to be here when those discoveries arrive, if you want to follow every James Webb update, every atmospheric breakthrough, and every new clue about this extraordinary world, make sure to subscribe, turn on notifications, and stay with us. Because we are closer than ever to answering humanity's oldest question, and the next piece of the truth could drop any day now. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.